Hello, my name is Cameron Hurd, and this is my report, my third lab in my Physics 2211 course. Here we were given a star of mass 2 times 10 to the 30th kilograms orbiting a black hole of unknown mass located at the origin. The star's position data as it completes an orbit around the black hole is given and is used to generate its trajectory in GlowScript. Here we are to analyze the star's motion, go find the net force acting on the star, and then use that to go estimate the mass of the black hole. This is significant because in previous labs we have been given physical quantities and a net force which we use to go predict future motion, but in this case we are given the motion of the object and we're using that to see if we can backtrack in a sense and go figure out some unknown physical quantities and the net force. The objective in this case is to develop a computational model that computes the net force and mass of the black hole and consider how an object's motion is related to the net force acting upon it. The fundamental principle involved in this lab is Newton's second law, or alternatively the momentum principle, which states that the acceleration of an object is directly proportional to the magnitude of the net force acting on it, and inversely so to the object's mass. It also states that the object's rate of change of momentum is equal in both magnitude and direction of the net force acting on it. You can see the relationship between this here in this statement. In this model, we assume that the only force acting on the star is the gravitational force as a result of the black hole. The equation for the gravitational force represented here, the magnitude of the net force equaling the gravitational constant multiplied by the mass of the two objects involved, as well as the distance between those two objects squared. Here we plug in the value for the gravitational constant, we give the star's mass. In this case, for this model, we assume that the time interval between the imported position data points is a day, which I represent here in seconds. Here we are calculating the velocity from our position data values, and specifically the x and y components. I then calculate the initial and final velocities for each respective data point, and then use that to go calculate the momentum, which is the mass times velocity. I then calculate the change in velocity as well as the change in momentum, which I then use to go calculate dp dt. And if we go back, we see that the relationship between the net force and dp dt. Here we see that they are equivalent, which is why I plug in here that the net force is equal to dp dt. I then split the net force into its parallel and perpendicular components, the parallel component being associated with any change in the object's speed, and the perpendicular component associated with any change in the object's direction. The perpendicular and parallel components are also perpendicular and parallel respectively to the object's motion. Finally, I calculate the mass of the black hole by rearranging this equation right here to go solve for this mass, let's say, which in this case is the black hole. You can see this here. Here is the trajectory over time of the star as it orbits around the black hole. These numbers represent the model looping and estimating the mass of the black hole as it goes through each data point. Here we can go see its trajectory. These arrows represent the net force in orange, the perpendicular component of the net force in cyan, and the parallel component represented in magenta. So we can see how it changes in magnitude over time as it gets closer and further away from the black hole. And here we calculate the total net force as well as its parallel and perpendicular components. Averaging all those values that were calculated and modeled together, I get that the end final black hole mass that I calculated was 1.12 times 10 to the 34 kilograms. So we say that the net force is equal to the change in momentum over time, but what does that really mean? By definition, the net force is the sum of all forces acting on the object. By Newton's second law, as we've seen, that the net force and dp dt are considered equivalent in both magnitude and direction, but are not the same. They share a cause and effect relationship. A net force acts on the object, which changes its motion and therefore changes its momentum. And as such, their parallel perpendicular components are also equivalent. If a net force is going to the right, its direction is in the right, then we also know that the change of momentum is also going to be pointed in that direction and of the same magnitude. The magnitude of the cause is equal to the magnitude of the effect. The rate of change of momentum can be directly obtained and measured from observed motion, which we did in the model. However, the net force cannot because we cannot see forces. So instead, it is derived from the rate of change of momentum. So now we ask, what if? Is it possible for the black hole to have a different mass without changing the star's observed motion, assuming the star is still only affected by the gravitational force? The answer is no. As we can see by the formula here for the gravitational force, we see that any change in the mass would result in a change in the force. And as we've shown, the force is connected to the motion of an object, so that will result in a change in the observed motion. Thank you.